Here we go. The last video. Did you just leave? You left me. She left me. What? She doesn't want to do math with me anymore. I think it's the last video. All right, so doing this alone. She has returned. Iris got sad. Iris was like, he's sad. I'm sad now too.
No, sorry, Iris. There. It was a joke.
I only wrote. Oh yeah, I haven't started sharing my screen yet. I was gonna do it solo. It's the last video. De Moivre's theorem.
De Moivre.
De Moivre. You know, I didn't even know what this theorem was until I started teaching precalculus. It's like one of those things that's really cool, all about complex numbers, but like I never learned it. So hopefully we can teach it. All right. You've returned. Thank you.
Should we go by master since we're both masters?
We're masters. I'm a master in education, not math. But you're getting your master's in math. We were just talking about this.
Got the regalia got us thinking about stuff.
Wait, so why is mine yellow and yours blue? Do you know?
I don't know.
These are hoods, by the way, everyone. A hood that you don't wear, actually, like a hood.
Maybe because we went to the same school and we did the same program. So
exactly.
Theoretically, they should be the same, but maybe someone just ordered something wrong.
Maybe. What is today? Today is Blair's graduation.
Amidst cicadas. It was so fun.
Cicadas, the 2021. Congratulations. I don't know. 2021, congratulations, all seniors who have just graduated. Period. Natural numbers. That is why we're wearing this regalia. Look at me with my big words.
Wow.
All right. But today's topic is not about graduation. It is about De Moivre's theorem, which is an extension of complex numbers. To get to it, let's warm up with some complex number stuff. So I got some questions that don't really relate to De Moivre's theorem. They kind of do, but we'll get to that. Here's a question, open-ended. Write a polynomial function of least degree with real coefficients with the given roots 2 minus I, 2 plus I, and -4. What are you thinking? How can we get this thing?
So least degree means that we are looking for like x cubed.
Yeah, because we got 3 roots here. X, so we're looking at an x cubed.
But probably don't want to just start off with that because it seems like that would be difficult. Maybe we could leave things factored.
So I'm gonna go ahead and do the easy one. We got a root of
Oh, I wanted that one.
I'll make you deal with the other ones. Y times. What are the other 2 factors of this cubic that you've not claimed?
So do we need like a x squared happening?
Maybe. So we have a root of 2 minus I and 2 plus I. But we need real coefficients.
So can we put in like x minus 2 minus I and then x minus 2 plus I and then multiply it out to see if the i's go away?
Hopefully. Let's see.
Because it feels conjugate-y.
It feels conjugate-y. These are conjugates, 2 minus I, 2 plus I. And we've done something similar to this like a while ago. It was irrational roots. They came in pairs. Maybe with real coefficients, complex number roots come in pairs, and these i's are going to go away. Let's do it. Do you want to deal with those first or the x plus 4?
Conjugate complex conjugate pairs.
Conjugate
pairs of complex conjugates.
Pairs.
All right.
Have you considered a career in rapping?
No.
Anyways, how do you want to distribute this thing?
X to X.
Wait. So these are 2 trinomials, right? I don't want to deal with distributing two trinomials. I
Okay.
think, what do we get? Like 6 terms? Can we group this so that's really only 2 terms?
We could group the 2 minus i's.
Wait, but do you see this?
Oh, yes.
Right?
X minus 2's. And then
Minus
we
I,
get the
X minus 2.
minus I and plus I.
What do we call that?
Conjugate.
Well, if I said X minus 2 times X plus 2, and I distributed them.
It's a perfect square trinomial.
Close, close. Similar to a perfect square trinomial, but
Difference
better.
of squares.
Boom, 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 boom. Difference of squares. Right, well, actually, let me bring that back if I can. X minus 2, X plus 2. If I distribute this, we get X squared. We get minus 4, but we get minus 2X and plus 2X. Difference of squares. We have a difference of squares here. It's going to be X minus 2 squared minus
-1.
I squared, -1. So that's going to be a plus 1, right?
Lovely.
Look at that. We are now back in reality.
Back to reality.
Let's get this cubic. Let's get this cubic. X, how do you want to do this?
Do we have to?
No, we don't. Leave that to the viewer to distribute this thing and get a cubic. We do see that it'll be a cubic, right?
Mm-hmm.
All right. Plus dot. We'll leave it to the reader. But this does beg a question though. And you said it at the beginning. We have 3 roots, and you immediately knew that you were going to get a cubic.
Fundamental theorem of algebra, right? It's like one of those things.
Yeah, so we haven't talked about that yet. That's like a new idea, even though like it's the last lesson. But if I said, hey, how many roots does like this 6th degree polynomial have? What would you say?
6.
6. What is this fundamental theorem of algebra you're saying?
The degree of your polynomial is equal to the number of solutions that you have.
Like, let me do another hypothetical. X squared plus 1 equals 0. How many solutions does that thing have?
It doesn't have any real solutions. Just do have complex. So I guess do you want to call them roots instead of solutions?
Yeah, well, we can call them roots. We can call them solutions. I don't really care about that. But you're like getting to this big idea that given a polynomial of n degree, it has n fill in the blank roots. N what roots?
Complex.
Complex roots, right? They might not be real, but there will be, in the case of what I had written before, 6 complex roots. Okay, the question is, how do we find those roots? Let's proceed. Maybe we'll discover that question today. Maybe we'll answer that question today. Okay. Here's another warm-up just to keep our brains nice and flowing for what is to come on the next page. If one of the roots is 3, solve the equation over the complex numbers. What are you thinking?
So we should probably just do like polynomial long division, or I guess if you want to do synthetic division, you could too. I just always forget what the pattern is for that. So then once you divide that out, then you should have something nicer to work with.
Let's do it. But before we do it, how many solutions will there be?
There should be 3.
Of one of which is 3.
One
right?
of them is 3.
So I'm gonna divide out that 3.
Okay.
Let's just do it real quick. X squared, for the x squared over that. That's gonna give me x cubed minus 3x squared. Do a little bit of subtraction. Remember the subtraction in the parentheses? That feels like so long ago. We've come so far.
Yep.
Right, those go away. Check my math as I go.
Looks good.
Cool. Ooh, I never shared the link with you, by the way.
Yeah.
Let me do that real quick.
Because you're trying to not let me grab you the last day.
that was the plan the whole time. All right, we're at minus 10. Let's see, we want to do a minus 10x there. We're going to get our minus 10x squared. Bring down that 59. And then negative 10, that's going to be positive 30x.
Mhm.
We're subtracting these. So we got to be careful here. This is when the signs get all out of whack. 59 minus 30, that is 29. I have a feeling we're going to get something nice here. 87. And then, there's something wrong. I want to put a
Plus
3
29.
here, right? Don't I want, yeah, plus 29. Okay, this is good. This is good. I'm sorry. 29x and 29 times negative 3 is 60 plus 27, 87.
Lovely.
Minus 87, boom, 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 0, no remainder. We have x minus 3 times x squared minus 10x plus 29 equals 0. All right, what are these other two solutions then?
Well, 29, is that factor? Can we factor with that?
I don't think it's going to factor, right? Because do complex, we could try to factor over the complex numbers, but the
Sounds
answer
good.
here, because it's being found in the complex unit, is going to be complex. Ooh, I want to like figure that out one day. How to like factor. I think we should use the quadratic formula though.
Sounds good.
Okay.
X equals negative b plus or minus. Oh, do you want me to write it?
Negative b.
So positive 10 plus or minus square
There's
root.
that complex conjugates come in pairs idea.
Mm.
B squared
B squared
minus
is 100 for AC.
and 4 times 9, that's 8. 4 times 20 is 80 plus 4 times 9, 1836. So 116. I think that is where we know we're getting complex roots here.
121. Yeah.
All divided by 2a, which is 2. Boom. Here are our other roots. How do we rewrite this as a complex number?
5 minus, what's that? So 4 divided by 2 is 2i?
2i. And we can kind of like work backwards to double check our answer. But there we go. 4 plus or minus 2i minus 2i and 3. Boom. But the big claim here that 1 and 2 are trying to attempt to showcase, in addition to presenting some practice problems, is complex roots come in pairs. And the fundamental theorem of algebra states that an nth degree polynomial has n complex roots. All right, let's proceed. You feel good?
Yep.
All right. I got some problems for you. We're going to try to address this question. Now, to do that, we need to reflect on last lesson, which was we talked about multiplying and dividing complex numbers in their polar form. We're going to do just that here, but with exponentials instead. R cosine theta plus I sine theta squared. What's that going to be?
So the cosine, so we're doing.
Let me do this. R cosine theta plus I sine theta times R cosine theta plus I sine theta. We'll just do that once. The rest will kind of remember that. How do we multiply complex numbers in their polar form?
Oh man, there was something about rotation.
If you forget how to do it, let's think about what these numbers actually mean. 5/2 cosine I sine pi over 6. What does it mean to multiply the number 1 or any number by 2 cosine I sine pi over 6?
We're scaling it up by 2.
Scaling 2.
Pi over 6 rotation.
Yep. And then if I decide to then multiply by cosine I sine 3 cosine I sine pi over 3. So we started with some number. We dilated 2, rotated pi over 6. Then what do we do with this new number?
We dilate it again.
Okay. And then we
rotate more.
Okay. So if I'm going to multiply two complex numbers, I'm going to do what with their magnitudes and what with their angles? Multiply the magnitudes.
So we get r squared and then we get the angles added together. So 2 theta.
2 theta. Theta plus theta plus I sine 2 theta. Boom. All right, so what if I multiply by r cosine I sine theta again?
Well, then you just take what you had, multiply it by r again, so you get r cubed. And then
Okay.
you add another theta, so you get cosine 3 theta.
Ooh, okay.
Plus I sine 3 theta. And I think the pattern continues.
Yeah, but I'm going to be annoying and make you do the next 3.
Okay, that's fine.
What's how about to the
changing
fourth?
that to a 3?
Oh, thank you. Ooh, I like it.
R to the 4th cosine 4 theta plus I sine 4 theta. And then r to the 5th times cosine 5 theta plus I sine 5 theta.
It's about to do 4.
Wow.
But then I heard you in the back of my brain. You're like, changing that 4 to a 5. And then my favorite number, what is r cosine theta plus I sine theta to the 47?
40, is that because that's how old you are, Mr. Kurt?
I am not 47 years old, but one day this video might be watched while I am 47. We should definitely, let's hope that that is the case. Because if it's not the case, that means there was probably another pandemic between now and then.
Oh, like then we would like remake the video.
Probably remake. Yeah, I don't know.
Okay. Not like YouTube got taken down and like.
It was, taken over by Disney, and then Mickey Mouse is the ruler of the universe. Anyways, let's continue.
That Mickey Mouse right there that you have in your corner.
Oh, that is the one, and that's why he's here, because I'm just trying to get on the good side before they become the ruler. R cosine theta plus I sine theta to the 47th.
I'm writing it now, but can you say what I'm writing?
I can't see what you're writing.
What do you think I'm writing?
I think you're writing 40 r to the 47 times cosine 47 theta plus I sine 47 theta. All right. Right. This is going to be convenient, because if I said, hey, what's 1 minus I to the 47? That is a lot of work.
Yes.
But if we can write that thing in polar form, maybe it's not as much work. We'll get to that. Put a question mark there. Right? De Moivre's theorem states this fact: for any positive integer n, r cosine theta plus I sine theta to the n is equal to what?
Let's see. R to the n.
Oh, you're writing it?
Mm-hmm.
Cool. R to the n.
Sine n theta plus I sine n theta.
There it is. That's all it says. When I first learned this, I was all scared. I'm like, De Moivre's theorem. Whoa, complex numbers. This is going to be difficult. But that's all it is. That's all it says. That is De Moivre's theorem right there. And we will use this to answer that question about the roots, the n roots of an nth degree polynomial, which get a cool name, by the way. But we'll save that for later. The roots of something. All right, let's use this to do a few math problems. Well, you're going to use it explicitly like it says, and we'll also like reverse engineering it and use it backwards to find roots. All right, so find 1 minus I. Is that what I said? Wow, I'm proud of myself. I did not even like remember. That was completely a guess. To the 6th.
Okay. So then that's 1 and then down an I. So that's what? Can we say negative pi over 4?
I love it. I love it. Yep.
And then how long is that? It's root 2?
Root 2. Yep. So in a nutshell, what did you just do?
I converted rectangular to polar, effectively.
1 minus I is equal to root 2 cosine I sine negative pi over 4 to the 6th. And if we rewrite this as cosine negative pi over 4, I sine negative pi over 4, we evaluate cosine pi over 4 and sine pi over 4. It's going to be root 2 over 2. That root 2 is going to combine with the root 2, become a 2 over 2. It's back to 1. All right, so these are literally the same thing. One is just in its polar form. All right, use De Moivre's theorem for us.
Then we get 2 to the 1/2 power, and that raised to the 6th, so that's 2 to the 3rd, 8th.
I'm going to do this. 2 to the 1/2 to the 6th.
And then I'll write 8 down below. And then
Sweet.
that with negative pi over 4 times 6, and that was what, negative 3 pi over 2?
Yeah, why don't you write that down underneath as well? I wrote negative 6 pi over 4.
Cool. Now what? Are we done, or do we need to do more?
Well, what do you think? Do you like to leave it in its polar form and all its glory, or do you want to convert it back to rectangular form to like maybe geometrically see it in the plane? What do you think? How you feeling?
I think it's okay, because I mean, like, we do know that it's going to be like a negative 3 pi over 2, so it's going to go like around, and then it's going to be like up here.
Well, let's just do it. Let's just do it. What is cosine of negative 3 pi over 2?
1.
So it's going to be 8 times 1 plus I. What is sine of negative 3 pi over 2?
0.
0. Look at that. It's 8. That's cool. And what I like to think about is here's our little our plane. We start at 1, and then we're going to multiply by 1 minus I 6 times, which means rotate and dilate. So we're going to rotate root 2. Sorry, we're going to rotate negative pi over 4, dilate root 2. We're going to dilate again, rotate again. So we're going to rotate 1, 2, 3, 4, 5, 6 times. I think we did something wrong. Oh, we did, but we'll get to that in a second. We landed here, and we are 8 away. What should the answer be based on this geometry that I just drew?
8i.
8i. And actually, I'm going down here. Cosine of negative 3 pi over 4, negative 3 pi over 2. That's the x coordinate at negative 3 pi over 2. 0. Sine negative 3 pi over 2 is 1. So we're actually going to get
1i.
0 plus 1i, and we get I.
Nice.
All right, sweet. I'm glad we did that because we check our answer. Sweet. Awesome. Doesn't hurt. Doesn't hurt to check your answer real quick. By the way, everyone, those who are looking at this, Larson, pages 512 to 516. That's the textbook we have used in the past. I will get everyone the link to the, in my opinion, superior OpenStax text later. All right, let's proceed. All right. We just used de Moivre's theorem explicitly. Let's use it in reverse. We want to find the roots of 4i. If I said, what are the roots of 4, what would you say?
2.
2.
Negative
And the
2.
principal root is 2, but what's the other root?
Negative 2.
Negative 2. And we can talk about what the principal root is for complex numbers in a second. But the roots of 4 are negative 2 and 2. What is that equivalent to solving?
The x squared equals 4.
X squared equals 4. Exactly. So let's jump over to the real problem. What are the roots of 4i? And I want you to write this as an equation. We'll find out what the principal root is later, but what are all the roots? How can I write this as an equation?
So can I have x squared equal 4i?
Bingo. All right. Cool. All right. We're going to use de Moivre's theorem. We're going to try to find the roots of 4i. Are you writing or am I writing?
I just wrote that.
Awesome. Cool. Now we can find x, but x is a number. X is a plus bi. Or what's another way to write x if it's just a number?
Just the a component?
No. So I'm trying to think of the best way to phrase this, but one way to write x is a plus bi. What is the alternate way to write a number apart from rectangular form?
Oh, r cis theta.
Yeah. R cis theta. Okay. So we need to find a number that when squared gives us 4i. I'm going to replace our x with r cosine I sine theta squared equals 4i. We need to find an r, and we need to find a theta that make this equation true.
So R has to be 4.
Well, do this for me.
R needs to be 2.
So are you using de Moivre's theorem here?
Yeah.
So r squared cosine I sine 2 theta equals 4i. But right now you're comparing apples and oranges right now. What can we do that 4i?
We can convert that into polar.
Let's convert that to polar. What would that be?
That would be 4 cosine I sine pi over 2.
Its magnitude is 4 cosine I sine pi over 2. Yep. And the way I like to write it, I like to draw 4i in the plane and then do the trigonometry to get those angles. Right. This time it's very nice. It's on the complex axis. It's on the y-axis. But if it was like out here, I'd probably draw a triangle with its dimensions and use arctan. But anyways, I see you. You pulled that pi over 2 out of your brain.
Pure imaginary axis?
Yeah. What did I say? Complex? Anyways, 4 cosine I sine pi over 2. Now we're in business.
Because then r squared can be 4. So then r could be 2. And did we establish that we're doing positive r's from now on?
Yeah, and I think we did when we established complex numbers. Do you remember that? We said that our numbers are going to be positive. Our modulus is going to be positive, kind of like an absolute value. And our angle is what's going to kind of give it its negative or positive feel. Now that numbers are just in this complex plane, they're like, don't really have positive or negative because there's a new direction. We added a direction. So now like we don't just go to the left. We go to left and up or down. So is up negative? Is down negative? Anyways, r squared is 4.
And then 2 theta is pi over 2, which means that theta's got to be pi over 4, and r has got to be 2.
Boom. R is equal to 2. But we have made a glaring, not mistake, but is pi over 2 the only angle you could have given me?
No.
What could you have given me?
Pi over 2 plus 2 pi k, 2k pi.
Yeah, I'm going to add that there. I'm going to add it here. And I'm going to add it here.
So when we divide, we get plus pi k.
If you think back to trig, when we had 2 theta, we divided by 2. And it also impacted the 2 pi k. Here are our answers. The solutions to the square root of 4i is 2 cosine I sine pi over 4 and 2 cosine I sine. What would the next one be? What's pi over 4 plus pi? 5 pi over 4. For the sake of just doing it, let's convert this back to rectangular. What's the cosine of pi over 4?
Cosine of pi over 4 is root 2 over 2.
Root 2 over 2. So 2 times root 2 over 2 plus I. Is it also going to be root 2 over 2? The sine of pi over 4. So we get root 2 plus I root 2. That's one of our roots. And then this one's going to be 2, a little bit different. We're in the fourth quadrant now. We're going to get negative root 2.
Third quadrant.
Yeah. Negative root 2 minus I root 2. And those are our 2 roots. And one of them is the principal root. So our roots are root 2 plus I root 2 and negative root 2 minus I root 2. Which one do you think the principal root is?
Probably the one with the positive a component.
Yeah, and that's actually, boom, you got the definition. What do you think the definition of principal root is now?
Positive a component.
Positive a. What if there's 6 roots though, and there's multiple with positive a components?
And also positive b.
It's actually not that. Where is it?
1.
The principal nth root of x is the nth root with the greatest real part.
Mm.
And when there are two, for x real and negative, the one with a positive imaginary part. There you go. That is what it means to be a principal root. That's the real principal root definition, which still holds true for what is the two roots of 4. 2 and negative 2. 2 is the larger of the real parts. They both have 0 complex imaginary part, but there you go. This one's the principal root.
The realist.
The realist. Yeah, I guess that's what it is. The largest real. Can we walk around and when someone's like telling you how it is, can we say that they're the largest real instead of the realist? Okay, you don't like that. Not a fan. Okay. Let's do it one more time. What are and I have 7 problems here just to give everyone an idea of how much further we have to go. What are the 3 roots of 1 plus I?
Oh.
Let me see you go through it.
But does Moivre's theorem work with non-integer exponents?
So it does. The proof of it is not as simple as the one that we did. Currently not prepared to do it. So we could use Moivre's theorem actually, but we would need to use like that plus 2 pi k. That's going to be important. Do you want to do it that way? Just bring down the third and bring down the third into the angle as well. Let's do it. Let's do it.
And I don't want to, because we can just do our x cubed equals 1 plus I. Which
is basically what we did before, right?
Yeah.
We wanted to find 4i to the 1/2. And that's exactly what we did.
Okay.
So we can do that, yeah.
Cool. So then we have 1 plus I, so we got to convert that. So we get r is root 2. R be root 2. And theta be pi over 4.
Love it.
Too much.
Really. So we got r cis theta to the 3 is equal to root 2 pi over 4, and I'm not going to forget it this time, 2 pi k.
Nice.
Sweet.
So then we have r cubed is equal to root 2, and then 3 theta equals pi over 4 plus 2 pi k.
Boom. So I think that makes r equal to the cube root of 2, which is, I believe, the 6th root of 2, right?
Yes, because you're doing 1/2 times 1/3 your exponent.
And then 3 theta is equal to pi over 4 plus 2 pi k. And theta is equal to pi over 12 plus 2 over 3 pi k. And notice that this is going to justify why there are exactly n roots. What happens if I try to get a 4th root? Well, let's write it out first and then answer that question. So our roots are 2 to the 1/6 times cosine I sine pi over 12. That's one of them. 2 to the 1/6 cosine I sine. What's 2/3 plus 1/12?
Like 8 plus 1, 9/12. Was that 3/4?
9/12, 3/4.
Mm-hmm.
Okay, and then what is our 3rd root?
So we have 3/4 plus another 2/3. So that's 9 plus 8.
9 plus 8 is 17.
17.
12, which is 17 over 12. What happens if we try to add another set of
Pi.
what? Pi, thank you. What happens if we tried to add another set of 2/3 pi? What is 17/12 plus 2/3?
Then we're adding what, 4 times that, so 8 plus 17, 25 12. That's back to pi 12ths.
25/12 pi and pi 12ths are coterminal. They will output the exact same rectangular coordinate as 2 to the 1/6 pi over 12. We've exhausted all of the possible roots because we are just going to end in a cyclic pattern. But this process can be done for any number. Once we get to 3, we start to repeat ourselves. If we're looking for the 6th roots, once we get to 7, we're going to start repeating ourselves. So it is impossible to have more than n roots. And similarly, there will be n roots because we can always get a unique one until we become coterminal with the answers that we already have. These are the 3 roots of 1 plus I. These numbers that if you cube them, you will get 1 plus I. You'll get root 2 cosine I sine pi over 4. I don't really feel like rewriting them as rectangular.
No.
Yeah. But if you want to just evaluate what cosine of pi over 12 is, it's going to be some number multiplied by 2 root 6. All right. There's one more really cool thing I want you to experience about the roots.
Okay.
And I'm going to give them that name, roots of something, after this problem. Let's do this process one more time. And I think we're getting better at it. We're going to be able to do it a little bit faster. Find the 3 cube roots of -8. So
equals -8.
Okay.
-8 is 8, and then I.
Just so you know, you're breaking up, and I'm trying to interpret what you're saying in the choppiness. Did you say the angle yet?
Pi.
Pi. Got it. Okay. You're starting to smooth out.
Nice. So so we get r equals 8, and 3 theta equals pi plus 2k pi. So then, and that is pi plus 2 pi k over 3.
Boom. All right, our roots are 2 cosine I sine pi over 3. 2 cosine I sine, is it going to be pi?
And then
2.
5 pi over 3.
5 pi over 3. What do you notice about these 3 angles? Or these 3 numbers? What do you think? What do you wonder? What do you notice about these 3 numbers?
Well, one of them is on the real axis.
And it's 2, right?
Mm-hmm.
I'm going to go ahead and make my scale a little bit different.
Whoa, getting wild.
Boom. That's this one.
Okay. And then pi over 3 is in the first quadrant, and then the 5 pi over 3 is in the fourth quadrant.
Yeah, I'm gonna do this real quick. 2 cosine pi over 3, cosine of pi over 3, that's root 3 over 2. That's gonna be root 3 plus, I think 1i, 1/2 times 2. I think I did that wrong. It's going to be 1 plus root 3i. cosine of pi over 3 is 1/2. Sine is root 3 over 2. So 1 comma root 3. Root 3 is about 1.7, I think.
Cool.
Cool. And then the other one's going to be 1 minus I root 3.
So you get a conjugate pair.
We get that conjugate pair. That's interesting.
That's cool.
I like that. I don't think we're always going to get conjugate pairs, though.
Yeah, because we have the x equals 2 cosine and sine of theta of pi, which doesn't get a conjugate pair because
Yeah.
the
That's gonna be-
imaginary part is
Yeah.
0.
Yeah, we're not going to have plus and minus I. But here's what I like to do. I'm going to go ahead and draw these. They're all the same magnitude away from the origin, which is kind of required. But the angle between each, in this case, is what?
2 pi over 3.
2 pi over 3. And in every case, it's going to be the same angle in between.
Makes sense.
Yeah, so the roots of a number are all rotationally symmetric. The angle between them is always going to be the same. And their magnitudes are the same distance away from the origin. So no matter what number I give you, the roots will construct a regular polygon in the complex plane, always.
That's pretty cool.
We call these 3 roots and the roots of any number. There's the principal root, but as a group, which one's the principal root here, by the way?
The greatest real.
This one, right?
Yeah.
Yeah.
Which is
All
interesting.
isn't it? But all of them together are called the roots of unity. I think that's pretty. The roots of unity. So if you can find one root and you know the angle between them, which is just, what's the angle going to be for the eight roots of unity for the 8th root of some number? What's the angle between them going to be?
It's 2 pi over whatever you're doing.
Yeah.
Because you take a circle and divide it up into however many things you're doing.
Yeah. So the super fast way to get roots is to just know how many roots there are, which is just n, find the angle between them, and then find a root. If we knew that -2 was a root, which hopefully you did, what's the cube root of -8? -2. The other 2 roots are going to be 2 pi divided by n, I guess, radians away. Same magnitude. All right, how do you feel about this last problem?
Solve the equation and then graph the solutions. Okay.
So we're not going to do the whole thing
Okay.
for the sake of time. But let's get it started so it becomes the previous problems.
Okay.
What do you think we should do? Because now we're finding roots of like equations.
Can we, well, we know how many we're looking for, right? We're looking for.
What shape is it going to make in the complex plane?
A square.
Square. Okay.
And then, so what did we do before?
So when I said, hey, what's the cube root of -8? You set up an equation. X cubed is equal to -8. Can you make this something like that?
Well, you can divide it everything by 2 and then move the not x things over.
You divide by 2, and then move the not x things over. Boom. -1 minus I root 3. Here, we are finding the 4 roots of unity for the number -1 minus I root 3. And it will make a square in the complex plane. They'll all be 90 degrees apart, pi over 2 radians apart. And their magnitudes are going to be whatever the magnitude of -1 minus root 3 I is. And then you just got to find one root, and then you can graph them all.
Is it 2?
You saying is 2 one of them?
I think the magnitude's 2.
Magnitude's 2. So we're 2 units away on the unit on the 2 circle, the 2 unit circle, making a square. But we'll leave that as an exercise for the viewer, which brings us to the end, which I wasn't going to scroll down until I said that. What would you have done if I didn't scroll down?
I would have moved it up.
Yeah.
Did
you make a crab with a hat, or did you find a graduating crab online?
I Googled crab graduation, and that was
and you found it.
Third option.
We should start a school with all of our videos, and the mascot will be a crab, and we'll be the fighting crabs.
Sounds good. Or we can just try to make Blair's unofficial mascot be.
Can we not? I don't want to say I'm not a fan of our mascot, but I'd be a bigger fan of a crab mascot. Plus, I'm I'm kind of scared of crabs. Like, I feel like I would get closer to, my high school was a ram. I feel like I would get closer as a human being to a ram. If someone said, hey, come and pet this ram, I might do that. I don't know if I don't like getting close to crabs. They creep me out, and I'm kind of worried. I was eating crabs the other day, and I got a cut on my thumb.
They're vicious.
Crabs are vicious, and an excellent mascot is what we've learned today. I didn't realize it was the last video until I turned the recording on and told you it was the last video. Do you have any words of wisdom for the final video? That's a lot of pressure.
Oh man. Keep going to school.
Come back, please. come back. Right. Oh, how about what's good advice for a graduating class?
But they're not even watching.
That's true. But I'm trying to think of a different theme, and I have mine. This is just the beginning. How about that?
Pretty good.
I like that. If I do say so myself. All right. You want to close this one out?
Yes. I wish I had my crab.
Wait, do I have the? No. Oh, I do. Speaking of Mickey, a book just fell, by the way. Speaking of Mickey, got the crab hat. Oh man, this is I don't want it to end.
It's okay, Mr. Kirk, because you're also going to continue going to school.
That's true. This is just the beginning.
Well, I think it's started already.
Yeah. There's one more semester of pre-calc. It's not over yet.
It's not over.
Here we go.
Bye.